Okay, we begin our study of Chapter 8 with a section here on dilations. If you look at the targets, it says I can identify dilations, I can draw dilations, I can apply the principles of dilations to solve problems, and then I can dilate points in the coordinate plane. So this is going to remind you a little bit of our transformations unit at the end of last semester when we were talking about translations and rotations and reflections. Those are all rigid transformations. Dilations is not a rigid transformation, which is why it sort of gets included in this unit, and I think when we get to a few additional sections, you'll see the connection here between dilations and what we're going to study in this chapter, which is similarity. So to remind you, a transformation is a change in the position, size, or shape of a figure or graph. All right, and we've talked about that before. The three that I just referred to are all transformations. So a dilation is different because in rigid transformations, we preserved the exact size and shape of it, and we just moved it around someplace. A dilation is actually an enlargement or reduction of a figure proportional to the original. So keywords are enlargement or reduction, which means we're making it bigger or we're making it smaller. And what else is really key here is that we have to be proportional to the original. So you see when we look at some examples there, what that's going to mean. So for example, I might start with an original that looks something like this. I could call that A, B, C. They call the original the pre-image, right? And then if we were to take a dilation, it might look something like this. All right, this would be the image. All right, so this would be a dilation of that original triangle. All right, and the scale factor here comes into this idea of proportional to the original. So what the scale factor means, it is the ratio of the linear measurement, and by linear measurement, we could think of that as the length of a side. Linear meaning straight, linear measurement of the image to the pre-image. Okay, so a scale factor is the ratio of a linear measurement, meaning like a side, of the image to the pre-image. So for example, in this case, I could pick side DE. That corresponds to AB. So that should represent my scale factor. So for example, if this is 4 and this is 2, my scale factor would be 4 over 2, which is 2. Now, if it's proportional, those have to be the same. So therefore, EF would be the same as BC. So if I said this side was 8, right, this side would have to be 4. Because 8 over 4 still produces 2 in the same way that 4 over 2 produces 2. And then, of course, that would have to be the same as DF to AC. That's that idea that they have to be proportional to the original. These ratios have to be the same. All right, that pretty much guarantees that you have the same shaped figure, that it's just simply enlarged or reduced. All right, so our first target was to identify. And so this is probably the easiest one. We're just going to be looking at some figures and determining if it's a dilation. This first one is not, because you can see we didn't change the width here of the trapezoid. Really, it looks like at all, right? But the height here completely changed. So that is a complete change of shape. That's just not a reduction in the size. This would be, right? This would definitely be a dilation, right? They are the same shape, and it simply looks like one was just sort of enlarged, that these sides would be proportional. So that's a yes, that would be a dilation. All right, if you flip the page, right, look at these L's here. See what you think, right? Are these just an enlargement or a reduction? Is this one a reduction of this one? Probably not. You can see this one's taller than it is wide, and this one is not. So that is a different shape. Here, if we start here and go to here, I hope you can see that this looks like hopefully just a reduction. So that does look to be a dilation. Again, they have to have the same shape, just be enlarged or reduced. Our second target is to draw dilation. So as I told you before, you're going to need a ruler to do these. All right, I'm going to let you draw your own triangle. So using your ruler, right, don't draw anything that's too big here. I'm just going to draw something that looks like this. If you draw it too big, you're going to run out of room on your paper. So it says draw a triangle and a point outside the triangle. So pick your point fairly close to the triangle. I'm going to put mine over here. All right, that point is going, I'm going to call it C. That's going to be the center of dilation. All right. Use a straight edge to draw a line through the center of the dilation and each vertex. So here are my vertices. I'm going to darken them so we can see them. I'm going to take my ruler and I'm just going to draw a line starting at C long enough through each one of those. Okay, and if you have trouble keeping up, remember you can pause this video anytime. All right, so that's step 2. Step 3 says we're going to use a compass. We're not actually going to use a compass here. I'm going to have you actually use the ruler. Notice we're looking at a scale factor of 2. So what that means is we're going to look at this distance. Let's label this point P. Let's measure this distance. I'll use centimeters. That might be easier. If I measure that distance, I would say it's about 1.2 centimeters. I'll even mark it for you here so you can see 1.2 centimeters. If I have a scale factor of 2, that means I now need to multiply this by 2 and go out that far. So I would take 1.2 times 2, which is 2.4 centimeters, and I'm going to go out from the center. So I'm going to go back here and I'm going to mark 2.4, which looks to be right about, I did not measure that right. That was not 1.2. I apologize. I can't read my ruler. That was 1.7. That's not very helpful. Sorry. 1.7 times 2 would be 3.4. So let's try that. It is good if you can read a ruler properly. 3.4 puts me out about here. And you should be able to eyeball this, because if you are doubling the distance, right, the distance from C to my new point should be double the distance from C to P. That's how I knew immediately when I was going to put my point here that something was wrong. So let's call that my new image. Let's call that P prime. Now you're going to do that for each one of these. So if I measure the distance to this next point, let's see if I can do it right here. I have about 2.8. So if I take 2.8 and I multiply by my scale factor of 2, that's 5.6 I'm going to go out. So 5.6 puts me about here. And then my last distance here looks to be pretty close. It looks like 2.8 again, so I'm going to go out 5.6 again. Okay, so for example, if I called this Q, I could call this Q prime. You could call this, I don't know, R and R prime. Now, if I connect my new points, I should have a dilation by a scale factor of 2. Okay, so my new triangle right here, this is my dilation with scale factor 2. What we learned on the previous page is then those sides should represent that same ratio. So for example, let's calculate PQ prime. PQ prime is about 6, or P prime Q prime rather, right? And PQ here looks to be about 3. So that ratio would be 2, which is good because that's what my scale factor is. And I should be able to do that with any pair of sides. My scale factor should come out to be 2. All right, so that's how we draw it. All right, so we'll practice again in a minute, but let's fill out this box on the bottom. A dilation is a transformation in which the lines connecting every point P with its image, P prime, intersect at a point C. So every time I connect these 2 points, or these 2 points, or these 2 points, those lines intersect here at a point C. That point is called the center of dilation. The ratio is, we could say, CP prime to CP, and this is the same for any point P. So if I took CR prime divided by CR, I should also get that ratio. And CQ prime divided by CQ, that should all give me the same ratio, which of course we know what that ratio is. That's my scale factor. That's 2. All right, so the scale factor of the dilation, we could think of it as this. We can also think of it as P prime, Q prime, this linear measurement over the pre-images linear measurement, PQ. So this to this should also represent 2, as does this to this, or this to this. All right? All right, let's flip the page. Let's try drawing another one here. So draw the dilation of the triangle with a scale factor of 1/2. So if you remember, the first thing we did was to use our ruler and draw a line through the center of dilation and each vertex. So I'm going to do that. There's P to A, P to C, and P to D. All right. And then the next step is to do the measuring. Notice this time my scale factor is 1/2. So I'm going to measure P to A. All right, so PA is, let's see if I can get it right this time. It looks like maybe 6.2. My scale factor is 1/2, so if I multiply by 1/2, my new value is only going to be out 3.1. So from the center, which is P, I'm going to find a point 3.1 out. That's my A prime. That's my new image. My scale factor is 1/2. So if this is my original distance, I'm now only going out 1/2. So I'm going to do that on each of these. If I measure the distance to C, I'm going to call that 4.8. So PC is 4.8. If I take that times 1/2, that means I need to go out 2.4. That would be right here. That would be C prime. Now I'm going to measure P to B. That one looks like about 6.2 again, so it's similar, so I'm going to go out 3.1. That would be my B prime. And now I should, if I connect, have my image with a scale factor of 1/2. So think about what that scale factor means. That means PA, right, to PA prime, that distance should represent 1/2. I'm sorry, that would be PA prime to PA, PC prime to PC, PB prime to PB. It always starts with the new image over the distance to the old image. I could also take AC prime, so I could also think of my scale factor as A prime C prime over AC, or I could think of it as C prime B prime over CB, or I could think of it as A prime B prime over AB. All of those represent the scale factor, which we know comes out to be a half. And if you check your measurements, you should get that. All right, so I'm going to leave this next example for you to try again when you want to. Right, it's the same idea. You're going to do scale factor of 3, so you would connect P to A, P to B, and P to C, measure those distances, and then multiply them by 3 to get your new points. It's going to get you a big triangle right here on your paper. All right, the third target was sort of applying these principles of dilations in problems. So if you read this first example, an artist is creating a large painting from a photograph by dividing the photograph into squares and dilating each square by a scale factor of 4. All right, so let's circle that there. Scale factor of 4. So the photograph is 20 by 25, and I'm dilating that by a scale factor of 4, right, to get the painting. So if I take 20 times 4, that makes this side 80. If I take 25 times 4, that makes that side 100. So my new painting is 100 by 80, and it asks for the perimeter. So the perimeter would be 2 times 100 plus 2 times 80. That would be 360. All right, let's look at the second one. On a sketch of a flower, 4 inches represents 1 inch on the actual flower. So we're looking at the sketch is represented by 4, and the actual flower is represented by 1. So we could think of a scale factor. I'll show you 2 different ways to do this one. We could think of a scale factor as the sketch over the actual, and that is 4 to 1. Then it says if the flower has a diameter of 3 inches in the sketch, so the sketch has a measurement of 3, what's the actual? All right, so that means when we multiplied something by 4, we ended up with 3 inches. So the actual times 4 should get me the sketch, if you want to think about it that way. Well, I know the sketch comes out to be 3. There's my scale factor. If I'm looking for the actual, that should come out to be 3/4 of an inch. For those of you who really prefer ratios, you could think of it as 4 is to 1, and then you could say, well, this is the sketch, this is the actual. I know the sketch is 3, and I'm looking for the actual, so I could say 4x is 3 and x is 3/4. That would be the measurement that goes with the actual. So whatever you prefer there, you can use a ratio method, or you can use kind of a multiplier in as the scale factor. So that's sort of the problem solving piece. The last piece we're going to look at is how we apply it to coordinates. This is pretty easy too here. So it says dilate the point 1, 2. So let's find that point 1, 2 by a scale factor of 3, center at the origin. All right. So I want you to look at what we've done to get here. All right. We're at the point here. Let's mark it 1, 2. We went over 1 and up 2. Now if I'm dilating that by a scale factor of 3, I have to take that pattern times 3. So back at the origin, all right, you don't start from the end point, but from the center, I'm going to do that times 3. So over 1 up 2, over 1 up 2, that would be my second one. Over 1 up 2 would be my third one. That would be my dilated point. Let's see where I'm at. This is at 3 and this is at 6. So 3, 6 would be that dilated point. All right, let's look at this one. If I have this point 1, 2 again, from dilated from the center, from 0, 0, notice this time it's -3. So now I have to reverse that pattern 3 times. And remember, I'm always starting at the center. Just like I did here, I did the pattern 3 times. So now I'm going to reverse the pattern 3 times. So instead of right 1, up 2, I'm going to go left 1, down 2. That's 1 pattern, 2 patterns, 3 patterns. That would put me at what? I think that's -3, -6, and that would be my dilation. All right, now look at, though, I think we can come up with a rule pretty easily. We started at 1, 2, and we dilated by 3. What do you do to 1, 2, and the number 3 to get 3, 6? I hope you can see that all we did was simply multiply the 3 in to each one of those values. So as a general rule below, we could say dilating the point xy by a scale factor of k from the center just leads to k times x, comma, k times y. Whoops, I'm not on the screen, sorry. So you're just simply taking your point and you're multiplying in the scale factor. Let's see if that works for the negative. Look up here. We had 1, 2, and a scale factor of -3, and we ended up at -3, -6. It looks like we just took that -3 and multiplied it in to get this. All right, so if the scale factor is a negative number, the image is equivalent to a scale factor of k with a 180-degree rotation. And to get the point, it's just -kx and -ky. And the 180-degree piece is just showing you here that we went 180 degrees in the opposite direction. That's what a negative scale factor does. So for example, if I picked xy, right here, and I picked a scale factor of, let's say, -2, I'd go, whoops, where am I here? I'd go back, whoops, I went 3 and 2, yep, and then back again, and you can see the 180-degree rotation. All right, so it kind of combines that idea of rotations and dilations together. All right, so quickly, we don't have to graph these then every time we want to dilate. If my scale factor is 2 and I want to know what happens to my image, I can just simply multiply in that 2. So x would be 4, -2, y would be -8, -6, and z would be 6, 4. Similarly, if I had a scale factor of -1/2, I can just multiply it in. So d would be -1, -2. E would be what? 3, -1. And F would be 3/2 and -4. And that's it for this lesson.